Hello dear, good morning and welcome back to my lecture on mathematical foundation of robotics. And as you know, we are discussing how to model humanoid as well as cobot. And in that context, what we have described in my earlier lecture, that how to mathematically model the forward kinematics problem of a cobot as well as humanoid robot, that is which is known as Baxter, and this is what the robot Baxter looks like. And in detail we discussed about the difference between industrial robot and a cobot or a humanoid robot. Although I am telling cobot or a humanoid robot, not necessarily that all cobots will be humanoid robot or all humanoid robots will be a cobot. Okay, that will depend on some of the characteristic features which I have already described and I will describe again. So in that context of modeling Baxter type of industrial robot, you have learned what is redundancy and why it is required, and actually redundancy makes our problem of mathematical modeling problem, control problem difficult, but it gives well appreciated dexterity, okay, which all of us want. And so that's why normally humanoid robots have redundancy, and Baxter also have redundancy. It has 7 degrees of freedom instead of 6 degrees of freedom. Okay, so industrial robot modeling, you know, by this time you now also know at least to the extent of detailed forward kinematics solution for Baxter type of cobot as well as humanoid robot. Now in this video lecture I will introduce you with another humanoid robot. It's not a cobot, it's a humanoid robot, that is called NAO, which become very popular in education and research community, and because it has many sensors and easy to control, easy to program, it can interact with human, so all kind of experiments can be done using NAO robot. Also NAO robot has been installed in several organizations to welcome people and to have some kind of have some kind of attraction, to create some kind of attraction to the people visiting those places. So all kind of things, actually for all kind of things the NAO robot became somehow popular. Okay, so we will discuss how to model NAO robot in my subsequent lectures, and we will talk in such a generalized way that once you know how to model Baxter type of robot, NAO type of robot, okay, then you will be able to model any type of robot given to you. Okay, and as you know, for modeling any robot you need to understand the anatomy of the robot, means how the joint moves, where the joints are located, how they coordinate, all kind of things you need to know. And I will introduce you with a short video that which will make you clearly understand how NAO robot actually works and what is the anatomy of NAO robot. Okay, so let us watch this video. So today I am going to show you the degrees of freedom of NAO. We have a fleet of NAOs, actually. NAO robot, it's a cobot or humanoid robot, whatever you can call. No, it is actually, sorry to say, it is a humanoid robot. It's not. We have divided it into 3 zones. Head zone. Head has 2 degrees of freedom. Head yaw, head pitch. And then right arm zone or left arm, whatever, it has a symmetry. So it has shoulder pitch and roll, elbow yaw and roll, and wrist yaw. So how many degrees of freedom? 5. 1, 2, 3, 4, 5. And the right leg zone has 6 degrees of freedom. This is interesting. This is hip yaw pitch, 1 degree of freedom. Your pitch
And
is
this
one
joint
degree of freedom. Please.
is a
note it
shared
down.
joint with torso, and then you have hip roll and pitch.
And
knee
hip,
pitch,
your pitch
ankle
is actually a
pitch
shared
and
joint,
roll.
which you will
so
see
ankle
after.
2, knee 1, 3, 4, 5, 6. So 6 degrees of freedom the leg has. Now let us see those degrees of freedom. Okay. You see, this is head. Okay. Head yaw and head pitch. Now come to the hand. Okay. So see, this is shoulder joint. Shoulder joint has 2 degrees of freedom. One is this, another is this one. Okay. Now come to the elbow. This is elbow joint. It has 2 degrees of freedom. It's a visible joint, and these are the 2 degrees of freedom. One is this, another one is this. Okay. And this is wrist, has 1 degree of freedom. So wrist 1, elbow 2, shoulder 2. That is 5 degrees of freedom on right hand, 5 degrees of freedom on left hand. Okay. Now to show you the leg degrees of freedom, I need to make the robot in
the lying position.
Right?
So robot is in lying position as if in operation table, so that
see
we
carefully.
can
Okay.
look around with all the joints.
Coming to
See
the
carefully.
hip. So this is actually, this is the joint. This is the joint, okay, which is
This is
shared by
shared joint.
torso and hip, which we are calling hip yaw pitch. So this is one, and then this is another one at the hip. So this is the axis, okay. And another one is, you see, this is
This is the axis of rotation.
okay.
This is the
So this is one, this is another one, and then here you have seen, right? Okay. Now here this come to the knee. Knee has 1 degree of freedom. Okay. And then ankle joint. Ankle joint has pitch, and then okay.
you can see more clearly here.
And this is an axis, another axis of rotation. Okay.
So you can see.
You can see. I'm just constraining it so that you can see. Okay. So these are the 6 degrees of freedom each leg has, and 5 degrees of freedom each arm has. Okay. Well, again, as you know, grammatically, not 25 degrees of freedom, it has 6 degrees of freedom and 19 degrees of mobility. Okay. So clear. Now we'll show you now in action. Okay. Now we are showing now in action. We have seen already the degrees of freedom, so it's listening, you see. Now stand up. Then sit down. So in fact there is a choreograph software. Using that you can write lots of programs. Using even the model, forward kinematics model, you can make now walk, now dance, whatever you want. Very interesting thing. It's a programming exercise, and we'll talk during lecture. You can do many things. Okay. So it is listening. It has a lot of sensors. We'll talk about that. But right now, the anatomy of NAO should be clearly understood. Bye.
Well, so you have seen that what different kinds of joints NAO robot has, which is a typical humanoid robot, okay, and where the joint angles are embedded, that also you have seen. So it has actually this kind of this is a skeleton structure, means how the joints are arranged, has been shown here. So this is now robot externally looks like, and then you see there are two joints, head yaw and head pitch, and you see these all these actually degrees of freedom are revolute type. Okay, that means they are rotating type. And as you know, the convention is that yaw, pitch and roll, these are three again revolute joint. And just look at my wrist. So if this kind of motion is there about an axis of rotation of this, then it is called yaw motion. Okay. Then consider another axis, axis of rotation, and if I rotate my wrist like this is roll. And consider another axis, z axis, about which if my wrist is rotating in this way, then it is called pitch. So pitch, roll and yaw. These are the three conventional name of three revolute joint. Okay. And this now robot has all revolute joint. Okay, so they are using this convention. They have been named like head yaw and head pitch. That means head can rotate like this, just like this. Okay, and pitch. Okay, so there are so many names of rotating joint, pan and tilt and all kind of things, right? So in case of now, it is head yaw, head pitch, and as long as you understand they are revolute joint and they are named as per convention, it is fine. And then this is shoulder pitch and shoulder roll. These are the two joint I have shown you in the video. Then elbow yaw, elbow roll. Okay, and then you have hip yaw pitch, and the same joint is being actually shared by the leg. And then you have hip roll, hip pitch, knee pitch, ankle pitch and ankle roll. So these are the degrees of freedom now robot has. And this is the internal skeleton, and as you know, the modeling technique remains the same. Okay, that means we need to assign coordinate frame. Z axis of the coordinate frame will be assigned along the rotation. Okay, along the direction of the rotation, because rotation will take place about that Z axis. So wherever you see axis, you put Z. So you see this is head joint 1, head joint 2, because 2 degrees of freedom. Each joint is providing 1 degree of freedom. Head yaw and head pitch. Okay, and then typically it has an axis of symmetry, just like our cobot Baxter. It has also axis of symmetry. So this is right hand, this is left hand, this is right leg, this is left leg. So these are the symmetrical limbs which has been designed. And now you will have to assign coordinate frame. And as I told you that wherever you see joint axis, your coordinate frame, you see, this is the Z axis of the coordinate frame. Okay, okay, and this is you see this is one joint. Okay? So Z axis will be assigned in this direction. This is another joint. Z axis will be attached in this direction, which has been shown here, and all kind of thing you already know. This is left shoulder. Okay, left arm. Okay, this is shoulder joint. Two degrees of freedom. Then again elbow. Okay, and then wrist. You have so as many degrees of freedom, that many coordinate frame has to be attached. Same story is for leg also. Okay, so please try to understand very clearly that seeing the coordinate frames, and you see which coordinate frame where is attached has been shown here. Here is the coordinate frame. Okay, so another coordinate frame attached here. Okay, so to reduce unnecessary parameter and to capture effectively the rotation correctly, so this kind of coordinate frame attachment is done. This is known to you. Okay, so that their origin will remain same, only one will rotate about another, all kind of thing. As far as possible, we will continue and we will show you that as far as possible we want that the de Hertenberg parameters should be 0. Okay. More clearly, we are discussing now humanoid having 25 link. Okay, so this is the signature of the NAO robot, which is used for mainly education and research. And you see very clearly we have shown here at the torso of the NAO there is a coordinate frame which we can call as a home coordinate frame or inertial coordinate frame. This is inertial coordinate frame. Okay, or home coordinate frame. Okay, so this is z-axis direction and this is x-axis, that means it is directing towards the front. So the front of the NAO robot, z-axis is vertical and y-axis is from right to left in this direction. Okay, so links definition. Okay, joint names, that is a point called torso located at minus 120.50 z millimeter from head yaw. So you should be able to understand what does it mean. It is minus 126.5 millimeter. Z means along z direction and in the minus z direction from head yaw. Okay, so it is a head joint, head yaw, z axis is in this direction, and you see torso where this is located. So where is the rotation, where is the origin of the torso? At a distance of minus 126.5 millimeter from head yaw. Okay, so head yaw you have seen, head yaw joint. Okay. Now x-axis is, as I told you, is positive towards NAO's front. So this is the front direction of the NAO. Front. This is back. This is okay, and y is from right. This is right hand, right to left, and z is vertical. So x y orthogonal, x y z orthogonal coordinate frame. This is the way it has been oriented, and its origin is at torso. Okay, and torso's address is this. Now look here that upper arm length. So these are the, when the manufacturer will give you the robot, you will know the specifications will be given by the manufacturer. Okay. So here you see body part of NAO and is the dimension. Upper arm length 105 millimeter, lower arm length 55.95 millimeter, hip offset along Y, hip offset along Y, okay, along Y direction 50 millimeter, hip offset along Z, so it has two offset. Thigh length is 100, TBL length, you see, TBL length is 102.9, foot height. So all these are depicted here. 45.19, hand offset X is 55.95, hand offset Z 12.31, shoulder offset Y 98 millimeter. So all these data are giving in the manual of the NAO, which you can see. Okay. So anywhere you can see. So originally, as you know, NAO robot was developed by a French-based company, headquartered located in the Paris, and the company name was Aldebaran. Okay, but afterwards, SoftBank Robotics procured that company, and then SoftBank Group actually, and the name of the robot became SoftBank Robotics. Okay, company name was SoftBank Robotics. So that is the little bit history. All this will be given by the company. Okay, so after getting these dimensions and everything, your job as a modeler is to develop model. So these are again, so what you will have to do, you see, divide and conquer, because it is complicated, so many joints are there, so we divide and try to divide and conquer principle, right? We divide into several groups, and then we try to develop model for the group itself. Okay, in that context, so this is head. So head has head, yaw, and pitch. Then you have right arm, and you see you have right shoulder pitch and roll, elbow yaw and roll, and wrist yaw. In the left arm also has the same degrees of freedom. Left shoulder pitch and roll, yaw, elbow yaw and roll, and wrist yaw. And all these degrees of freedom you have seen in the video, which I have played. Then right leg, again right and left leg, they are again symmetrical. So right is hip yaw pitch, knee pitch, ankle pitch, ankle roll. Okay, same is the story for left leg. So having clearly and correctly assigning the coordinate frame, same old story. Wherever you can see the joint, Z axis has to be assigned in that direction. Okay, and in the direction of the link length, X axis will be attached. Okay, and Y axis will be completing the orthogonal coordinate system that you know. And this is the same transformation matrix between any two link I and I minus 1. Okay, so let us try to now make model. Let us start from the head. Okay, very simple. Okay, so this is what you will have to do. First you will have to create genome of head, Hartenberg table for head. So that's I have created here. I link alpha I minus 1 is a twist angle, as you know, and AI minus 1 link length, DI is the distance between two successive common normal, and theta I is actually the variable parameter, because now it is only revolute joint. Okay, you call it pitch, roll, whatever, yaw, they are revolute joint. So this theta column will be variable only. All this will be fixed as now is given to you. Okay, so for link 1, you see we have assigned link 1 in such a way at the head. This is link 1. This is link 1. Okay, okay. This is the link 1. So that is Z-axis direction. Okay, and alpha because this Z1, and you see for this link length, so the Z are collinear. Okay, so alpha is 0, AI is 0, DI is 0, and only theta I head. Okay, so this will be the variable. Okay, so now can revolve head like this. Okay, so this is yaw, and then for link 2 coordinate from this is head join 2. Okay, and you see the Z axis of the head joint. This is the Z axis, and this is the Z axis for zeroth link coordinate frame. Okay, so it is in this direction. If I am looking from here, looking, okay, so what is this direction? It is clockwise, so it will has to be minus, okay, as per convention. Clockwise rotation, looking from the direction, this is the direction of the, you see, it's clear, I believe, right? So this is our Z0, Z1, okay, so Z0 and Z1, so Z1 is rotated in a clockwise direction by 90 degree, so it will be minus pi by 2. All other parameters are 0, and so whatever rotation will be there in theta 2 head, with this minus pi by 2 always have to be added, because this is the structure, okay. So that's it. Only head has 2 joints, and we have correctly assigned coordinate frame, inertial coordinate frame. With respect to that, the joints are moving, and it has been captured by this, okay. And so what will be the model for head? I have coordinate frame, that is the coordinate frame attached correctly. Transformation matrix I have deduced it already, see in my earlier lectures, and I will just enter row wise all the parameter. They are day parameter. This is only variable, okay. With motion, this will only vary, this will only vary. These are all geometrical parameters. It's very simple, okay. So what is transformation matrix of link 1 with respect to 0? Just read this, put this parameter here, and you get the simple matrix. Then come here to get transformation matrix of link 2 with respect to 1, and just put all these variables, all these parameter values in this matrix, and you generate this. So this multiplied by 0 means this is becoming, this element is becoming 0, this element is becoming 0. So there are many, this is a sparse matrix kind of thing. So many zeros are there. It's good, right? So you will have less computation, and specifically for that, this 3 coordinate frame has been attached judiciously. Okay. So this is what you are getting. So this is my model for NAO robot head. So similarly, I will move forward, and I will model right arm, either right arm or left arm, because they are same, and left leg or right leg. Okay. So in my next video, I will try to in this divide and conquer situation, I will try to show you the model of the robot arm, leg. Today I have shown you head. So all these models, when ready, now you can just simulate. You can write software like choreograph software, and you can simulate this motion, and all kind of dancing, robot interaction, all kind of things can be done. And a little bit more about the stability. It has a gyro rotor at the belly, that is in the torso, which you cannot see, but it gives, it's extremely high stability. It's very unlikely that it will fall down, okay. So if the gyro rotor is on, it gives additional stability, gyroscopic stability to this NAO robot, okay. So this is something I wanted to tell you about all the how to model NAO robot. And once this forward kinematics for head, for arm, that is for leg are done, then entire robot is known to you. So here is, the inertial coordinate frame or home coordinate frame, and now actually can walk. So you need additional coordinate frame to actually capture the motion of the now with respect to, say, this is a coordinate frame I have attached. In anywhere in the room where anywhere in the room where now actually will be operated. Okay, sorry. So I will show you anywhere. Say this is one corner of the room. So you select a corner, you assign a coordinate frame, orthogonal coordinate frame. So you call it the reference coordinate frame. So you have a reference coordinate frame with respect to what, when now is working, you are able to capture its where the position and orientation of the inertial coordinate frame which is attached on the body of the now. And with respect to this, you can have all the addresses, all the relations of head, arm, leg, everything with respect to this, and this with respect to this. So ultimately, you can control now's motion. You can even write simultaneous localization and mapping, can solve simultaneous localization and mapping problem for now. All these things you can do. The most fundamental one I have shown here, how to make model with the now robot, and up to head today we have done, and we'll continue our discussion how to model now's arm, now's leg, etc., etc. First forward kinematics, and then we'll discuss all together what are the challenges of solving inverse kinematics for Dexter, for now all together, okay, and how to solve them. So with this I conclude, and thank you for your attention. Stay safe. Bye bye.